Hey there, Chem Scholars. Today we are going to talk about the periodic table. Okay, so a lot of people contributed this and deserve credit, and they're not going to get it from me. Okay, we're trying to keep this a little simple here this year, especially. So we're going to jump right to the main periodic table, which you kind of see behind me. Okay, which is organized by a Russian by the name of Dmitry Mendeleev. Okay, what a suave-looking gentleman, huh? Okay, Mendeleev organized the table according to properties, and he wasn't the first one to do it, but he was by far the most thorough. Okay, he didn't just study a few properties. He had a lab team that he had them doing all kinds of stuff. They studied dozens and dozens of properties of elements, and when he found elements that behaved in a similar way, he put them into columns that he referred to as families. Okay. And then from there, he organized them according to increasing atomic mass. Okay. With that in mind, he had gaps. Like, for example, let me switch views so you can see me a little bit better, dear. Yeah, that's better. Okay. For example, he knew that zinc had to be here. He knew that arsenic had to be here. But that meant then that there was a gap here because gallium and germanium did not exist yet. And he didn't worry about it. He just knew that there had to be more elements, and he left gaps, and he explained what those elements would be like, and actually led to the discovery of several of those elements. Okay, so he didn't worry about little inconsistencies or whatnot. For example, he had cobalt here, he had nickel here, and cobalt is actually slightly heavier than nickel. He just figured that the mass wasn't being measured right. Technology wasn't all that great back then. So he just said, don't worry about that. Someone will fix that along the way. We're going to leave the elements by properties. We're going to leave them there. Okay. So, for example, here's one of the elements. Oh, I forgot I clicked on the wrong thing again. Okay. So here's one of the elements. He called eco-aluminum, but we eventually called gallium. Okay. And you could see the properties that he listed there. You see that he actually kind of predicted pretty well what gallium should be like. He called it eco-aluminum, which just means beyond aluminum, because it was the next one in the column. Okay, but don't worry about that. Okay. Likewise, he did the same thing for germanium. He called it ecosilicon, and you see that his properties are pretty good. Okay, and there's a longer list than that. I just put a partial list up there. Okay, so Mendeleev did a great job, but again, he had those inconsistencies. It wasn't just nickel and cobalt. There's a couple places where the mass doesn't make sense. He said, the masses aren't being measured right. But the issue is really the idea of atomic numbers, okay? And so we have this guy, Henry Gwynn Moseley, okay, not Mr. Mosby, okay, Mr. Moseley, who comes in using this new technology and he finds atomic numbers. What are atomic numbers? Right, atomic numbers represent the number of protons, and in a neutral element, that means the number of electrons, okay? So he was actually able to figure out atomic numbers using these x-rays, and that's why cobalt comes before nickel, because cobalt has less protons, it comes before it, okay? So it had to do with that, and that's how the table came into being. And obviously, there are a lot more elements now than in their time, okay? Mendeleev was in the 1800s. Moseley was right around the turn of the century, around 1900, in the early 1900s. And now, technically, we have elements all we have here. The periodic table that I shared with you has all 118 so far. Whether there'll be more or not, we'll see as life goes on. This table's a little old, so it doesn't have it. This table is older than you. It's 2003. Okay, so that's why it's not there. But most of the elements down here that are listed and outlined in white are man-made elements. Okay, we don't do a lot with man-made elements. Okay, and I'll talk about them again in a little bit. Okay, so let's continue discussion here and talk about families. I use that word. Okay, you notice on the periodic table up here. Okay, let me actually zoom out again just so you can see me. Okay, up on the top it says group, and you see group 1, 2, 3, 4, 5, 6, 7, 8, etc., up to 18. Okay, groups are numbered, okay? But sometimes we refer to them as families. So group 2 could be called a family, okay? And it is, and we're going to talk about some of the names of those now, okay? So, okay, the first family are referred to as the alkali metals. So that would be lithium, sodium, potassium, rubidium, cesium, francium. Now you notice that I didn't say hydrogen, okay, because hydrogen isn't really a metal. So why is it listed there if it doesn't belong there? Hydrogen and helium are special. Eventually I'll talk about them, okay? So, hydrogen is listed there because it does have some similar properties, but it also has some similar properties to the halogens, okay? Come back to that, okay? So alkaline metals, group 1, okay? Alkaline earth metals are group 2. Now, similar name, I know. Alkali metals, group 1. Alkaline earth metals, group 2. Beryllium, magnesium, calcium, strontium, barium, radium. Okay? Then we're going to jump the other side of the table, and we're going to talk column 16. Okay? And yes, a couple of the other groups do have some names. Group 16, the chalcogens, not everyone talks about, but oxygen is so important, I always include it. So oxygen, sulfur, selenium, tellurium, polonium, those are your chalcogens. The next column over has a somewhat similar name, but a little bit more familiar, halogens. Okay, and we have fluorine, chlorine, bromine, iodine, acetine. Notice I didn't say iodine, okay? Little pet peeve of mine, okay? Would you say fluorine, chlorine, bromine? No, you say fluorine, chlorine, bromine, iodine, acetine, okay? The elements in columns tend to have similar names as well, okay? That's something that they try to do consistently, although some of the older elements don't necessarily fit in there, okay? But that's the facts. All right, so the very last column are referred to as the noble gases. Helium, neon, argon, krypton, xenon, radon, and technically this bottom one here, 118, is oganesson. You notice that they end with on. Well, not helium. Well, again, helium doesn't totally fit with them. It does, and it doesn't. Helium is, without a doubt, a noble gas. It's actually the most noble of the noble gases. But at the same point, because of something to do with its electrons, it very often fits in with this column here, group 2. But it's not a metal. But, the names, again, if you put helium up there, you have helium, beryllium, magnesium, etc. You hear that eum at the end. That's kind of where the naming came into play. Not a big deal. Don't sweat it. Okay? So those are the most common families, but there's a couple other little groups and things that we need to talk about. Okay? Transitional metals. Okay? So the term transition means you're between things. Okay? These elements are between energy levels. Okay? Now, typically, even though on this sheet, on the PowerPoint, it doesn't include zinc, cadmium, mercury, we'll probably just treat it as being there, okay? So transitional metals are all in here. But keep in mind, these two rows, see the stars? These two rows fit in there, okay? So the stars, we're really saying these elements fit in here. Why aren't they there? Well, because the table would be too long, okay? So they bumped it out and just leave it there. So you'll notice on the side here that we have numbers 1, 2, 3, 4, 5, 6, 7. There are 7 rows or 7 periods. These two rows fit. So this row fits in the 6th period. This row fits in the 7th period. Because they're rows, but they tend to be isolated, sometimes we refer to them as series. I'll use that term in a minute. But all of these are part of transitional metals, technically. Okay? There's a special term for it, but we're not going to go into that. Okay, now those two bottom rows are called the actinide series, lanthanide and actinide series. So La is an element called lanthanum. So the elements that come after it are referred to as lanthanides or the lanthanide series. The lanthanoids is another one. And AC is actinium, so the elements that follow that are referred to as the actinide series, actinides, actinoids. These two groups together are sometimes referred to as rare earth metals. And obviously the name says it all. Not too common on this planet. Okay? All right. Now, on my table, a little different color coding or whatever else, but on a table very often you'll see that there is some kind of color coding for states of matter. I did not do that on the one I sent you, but feel free to add your own color coding. Okay, so based on the table on the slide, I guess it's easier to look at that. You'll see that most of the elements are listed in yellow. Okay, the yellow elements would be solids at room temperature. Okay, the blue elements would be gases at room temperature. So you see there's, not a lot, but there's a few blue ones. And then there's 2 red ones. Those are liquids at room temperature. So there's only 2 elements that are liquids at room temperature, bromine and mercury. Okay? And then you'll see that there's a bunch of gray elements. Gray are man-made. We don't find them on Earth. We can only make them in a laboratory. Okay? So again, my table has a little different color coding. If you're in school, I can go through. It's still pretty much the same elements except for some of the man-made because, again, old table. But the idea is the same. Mercury and bromine are one color. The gases are a different color. The solids are a different color. Okay? All right. I kind of used the term metal already, and I guess we should really define it. Okay? We typically talk about metals as being those elements that are shiny or have luster. They're ductile, meaning that they could be drawn out into a wire. They're malleable, which means we could shape them very easily. They bend easily, and they are conductors. Okay, so that's what we define metals as. Most of the elements on the periodic table are metals. Okay, so if we were to go back to periodic, actually, let's just jump to the big periodic table. Okay, all of the elements up to around here are metals. Okay, there is actually. Let's jump to another picture just to make it a little bit easier to talk about that. So let me go to here and go back a couple slides and talk about these elements here. So you notice that we have these elements in purple. Everything to the left of the elements in purple would be metals. Okay, so all these elements all through here are all metals, and that would include the lanthanides and actinides. They're metals. Okay, then we have these let's go to the other side of purple. So on the other side of purple, we have a little almost like triangular wedge over here. Those are your nonmetals. Okay, so what are nonmetals? Well, nonmetals would be the opposite of metals, right? Instead of being shiny, they're dull. Instead of being malleable, which means bendable, these things are brittle. They break apart when you hit them. They don't bend. Okay. Instead of being conductors, they're poor conductors, or what we would call insulators. Okay, so those elements there are your nonmetals. And then the purple elements represent something that's a little bit of both. Okay, so let's go to talk about those real quick. We have the metalloids. Okay, metalloids have a mixture of properties. Okay, so at one point they included aluminum. There's usually drawn a staircase line on the periodic table. My big one doesn't have it, okay, but I'll go through that with you in a second, okay? And the elements that border that are considered to be metalloids. They're a little bit metal, but they're a little not metal, okay? For example, silicon is used in computers. It's a fair conductor, but at the same point, it is not shiny, and it's not extremely malleable, okay? So, not so good like that, okay? So aluminum, though, even though it kind of is in that area, is not considered to be a metalloid anymore. They just generally refer to it as a metal. Okay, so let's explain where that staircase would be. So on your periodic table, what you want to do is start up here to the left of boron and go under, down, under, down, under, down, under, down, under, down. Okay, so you just got to work your way starting up here and just snig it on down. That is the staircase line. So the elements that border that, like boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, and a couple of the man-made ones, we consider those to be man-made. There is some argument about a couple others, but aluminum is the only one that we have to worry about. We will not consider aluminum to be a metalloid. We will keep it as a metal. Okay? Now, last bit for today, let's talk about hydrogen and helium. Okay, so as I said, okay, sometimes helium is put in group 2 with beryllium, magnesium, etc. because of its number of electrons. Okay, it's the fact that it has 2 valence electrons. That's a term we're going to come back to tomorrow. Okay, these all have 2 valence electrons, so it fits. These all have 1 valence electrons, that's why hydrogen is there. But on the other hand, helium is very noble, and that noble means that they don't react. They used to be called inert gases. They call them noble because they're better than the other elements, okay? They're noble. They don't react with regular elements. They don't react at all. They're calm. They do the right thing, okay? So helium does fit in with the noble gases. That's why it's most often put there. Hydrogen, on the other hand, does kind of fit in with the halogens, okay? It is a little bit like fluorine and chlorine because it wants 1 electron to make it happy, okay? To make it more content, to make it act more like a noble gas, okay? So in that regard, being only 1 electron away from helium, it wants to be next to helium. So again, you could see tables where it's listed both ways. And honestly, there are tables where hydrogen and helium are just detached and put up on their own because they don't totally fit one particular location like the elements do, okay? So there's our ladder periodic table. Ciao for now.